So in the systems two, you come to the definitions. You know the definitions of proof. You cover also elementary properties of a group. Now we come to the and rings definition of ring and elementary properties of a rings. Now, now in the come to the rings, so we give some examples. With examples, it's word in that certain ring. So before in wording examples, suppose if we take an elements in a set in the ring. So in the set Z, N, Q, R, C, whatever be. Yeah, this is word. I given said N is the smallest set contains Z. Z is contain Q. Q contains R contains C. Means set of all a natural number is the smallest field compared to set of all integer. Set of all integer is a smallest compared to set of all a rational. Rational is field contains R. R is a real number. Real number is contained set of all complex. Means complex is extended field. That is the rare. N contains Z, Z contains Q, Q contains R contains C. Yeah, this is to know. We know this this to be. N is the smallest field. Now we come to this. If R is a ring, there exists an element denoted by 1, such that 1 into A is equal to A into 1 equal to A. So, any element multiply 1 itself is an element. Any element multiply 1 itself in elements. For all A belongs to R, then R is called a ring with unit elements. The element 1 in R is called a unit element of a ring. So, if you take a ring is a non-empty, the ring is non-empty. At least one element, that element should be a 1. If multiplying that elements is any elements, we get n elements. So multiplying 1 into A, that is we get a element. 1 is called unit elements of a ring. So this is what in a ring R. So by use that, I go for an examples, the rings examples. This set R consisting of single element 0. So R is non-empty. Single element is there. R consisting of a single element 0 with two binary operations defined by 0 plus 0 equal to 0 and 0 into 0 equal to 0 is a ring. This ring is called a null ring or zero ring. Simple definitions. R is a non-empty, at least a single element is a 0. 0 is there because Z is there, 0 is there. So 0 element. After the second definitions, a second example, the set Z of all integer is a ring with respect to additions, multiplication of integers. As a two ring compositions, ring is called ring of integers. Ring of integer. See, the two operations, addition and multiplication. Suppose if you take a Z equal to set of all minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, etc. See here, the set of all integer is a ring with respect to addition and multiplication. We go for the properties of a ring. We already know the properties of a ring. Here, if we take any two elements, belongs to the resultant elements also in Z. I take a product, any two product, the resultant is also in Z. 0 is there, additive identity is there. Additive identity is there, 0 is there. Inverse. If we get a 0 an element, minus 2 plus 2. So is 0? Yes. 2 is the inverse of minus 2. Minus 2 is the inverse of 2. 2 is the inverse of minus 2. Minus 2 is the inverse of 2. Similarly, 5 plus 5 equal to 0. Minus 5 plus 5 equals 0. 5 is the inverse of minus 5. Minus 5 is the inverse of 5. Here 0 is the additive identity. Minus 5 is the inverse of here. See, this word in Z, the property, what property in a ring? The property words in a set of all integer. So we come to the next is one more examples we have observed now. The set 2z of all even integer is a commutative ring without a unity additions and multiplication of integer being a two ring composition. So if we take a 2z, what is a 2z? Set of all minus 6, minus 4, minus 2, 0, 2, 4, 6. We observe here is in the set 2z, 1 does not appear. 1 is not appearing. So there is a no unity, no identity. No identity. Identity is 0 is there. Additive identity is there. There is no unity. Without unity, 1 is not appear. So is a ring. Is a ring. All the properties hold. Minus 2 plus 2 is 0. Minus 6 is there. Plus 6 is there. Minus 4. Add any two element again. Minus 2 minus 6. You get minus 6 is there. 2 plus 4 is 6 is there. 2 plus 3 is not there. 5 is not there. 2. So you add here elements. 2 plus 6 is 8 is there. So 1 into integer. So but no unity is 1 is not appear. But it's a ring. 0 is there. All other property hold. If you take a distributive property is hold. If you take a commutative 2 plus 4 equal 4 plus 2 minus 6 minus 2 plus of minus 6 equal minus 6 of plus 2 minus 6 plus of minus 2 again is same. Commutative exists, distributive exists, identity is there, identity is 0, but there is no unity. It's a set of all even integer. Now we come to the one more example. Set q of a rational number is a commutative ring with unity. So the additions and multiplication of rational number being a two ring compositions. Yeah, if you take a rational number, suppose if you take a rational number, 1 by 2 is a rational number, 3 by 4 is a rational number, add 1 by 2 plus 3 by 4. Again is a rational numbers. So 1 by 2 plus 3 by 4, again 3 by 4 plus 1 by 2 is a commutative. So is a commutative. Take 1 by 2 into 3 by 4. Again 3 by 8 again is a rational. See, addition is exists, multiplication is exists, product of a two rational number is a rational number, sum of a two rational number is a rational number, is unity. So we can write, we get cancel, we get a unity. 1 by 2 divided by 1 by 2, again 1 by 2 is a rational. 1 by 2 is a rational. We multiply. 1 by 2 is a rational. 2 by 1 is rational. 3 by 4 into 4 by 3. We get cancels, we get unity. Unity. This okay. Suppose if we take a, b, c is a rational number, a of b plus c equal to a into b plus a into c. Again is a rational. If we take distributive properties hold in the case of rationals, multiplying of times we get again a rational numbers. We come to the set of all a real number. Say set R of a real number is a commutative ring with unity, addition and multiplication of a real number being a two ring compositions. Similar as what passions is hold before that, the same passion is hold in set of all real number. We come to the extension field of a complex. Here we know familiar about sum of a two complex number is a complex number, product of a two complex number is a complex number, division of a two complex number is complex number, difference of a complex number is complex number. So 0 is there. 0 can be written as 0 plus I into 0. 1 can be written as 1 plus I into 0. 0 can be written as 0 plus I into 0. 1 can be written as 1 plus I into 0. So additive identity is there. Multiplicative identity is there. So distributive properties hold. Suppose if we take z1 plus z2 equal to z2 plus z1. So z1 into z2. Z2 into z1. Because z1 and z2 is a complex number. Z1 divided by z2 again is a complex number. 1 by z2 is also a complex number. 1 by z is also a complex number. So suppose if it z1 of z2 plus z3, so z1 into z2 plus z1 into z3 distributive properties hold. So in the case of complex number, see, I give all the example regarding set of all integer, set of all rational number, set of all real number, set of all complex number. Why not? I'm not discussing about a set of all natural numbers. But in the case of a natural number, here the natural number does not minus sign. No, there is no minus sign. 0 is not there. Suppose if you take 2 in a natural number, 3 is a natural number. 2 into 3 is a 6, is a natural number. 2 is there, 3 is there. 2 plus 3 is a 5, 5 is a natural number. Suppose if we take 2 minus 3, we get minus 1. Minus 1 does not hold in n. Minus 1 does not hold in n. Suppose 2 is there, minus 2 is there. Suppose 2 minus 2, 0. So 0 does not hold. Suppose negative is not there. So natural number does not hold in case of integer. It does not hold in the case of ring. So only a natural number is a ring, but only operations is hold. Only addition and multiplication. But other operation does not hold in the setup of natural numbers. The setup of natural. That is what I am saying in the previous. The natural number is the smallest field to compare all other fields. So that's the natural number does not hold. See, again, I am discussing very familiar A, B, C like that. Only two elements adding to each other. Suppose if you take a setup of a square matrices, equal sizes. You know the square matrix as a equal sizes. Let M be a setup of n cross n matrices. Their elements as real numbers. The entries are real numbers, either complex, either real or rationals. We already familiar. AB should not be equal to BA. Means A and B is a matrix, a square matrix. The commutative does not hold. AB not equal to BA. AB is not equal to BA. Is not commutative. But addition is exists. A plus B equal to B plus A. Okay. But composition I am saying AB not equal to BA is a ring with unity. Also there the matrix is A. Identity matrix is there. 1 0 0 1. Null matrix is there 0 0 0 0. So additive identity is identity 1 0 0 1. Null matrix 0 0 0 is there. So 0 matrix is inverse matrix is exist. Identity exists. Identity matrix is there. Null matrix is there. So what property hold in the ring? The matrix conditions is also hold. The matrix must be a square matrix. Matrix must be a square matrix. The set M of all n cross n matrices with their elements as a real number, either rational or complex or integer, is a non-commutative ring with unity with respect to addition and multiplication of matrices. The two ring compositions. These are all examples regarding the rings. Now, we come to extend these all examples. One item. Suppose we take a Z6. What is a Z6? 0, 1, 2, 3, 4, 5. Z6. See, I take a 2 in Z6. 2 in Z6. 3 in Z6. See, 2 is not equal to 0. 3 not equal to 0. 2 not equal to 0. 3 not equal to 0. Non-zero element. You are choosing non-zero element in Z6. But we productivity take 2 into 3. What's a 2 into 3? 6. 6 is 0. Because remainder is Z6 in Z6. 6 is 0. But you see, A not equal to 0. B not equal to 0. Product is 0. This is called zero divisor. Zero divisor. See, a non-zero element A of a ring R is called a zero divisor, a divisor of 0. There exists an element B does not equal 0 such that AB equal to 0 or B equal to 0. This is called a zero divisor. I come to the one more definitions. A ring R without a zero divisor. Without a zero divisor. If without a zero divisor, if the product of two non-zero elements of R is 0, R is not a 0. See, A not equal to 0, B not equal to 0, the product should not be equal to 0. Suppose we take in a Z6, similar Z6. What is Z6? 2 not equal to 0, not equal to 0, 4 not equal to 0. What is the product? 8. 2 into 4 is 8. 8 can be written as 2. 2 not equal to 0. See, 2 not equal to 4 not equal. Product should not be equal to 0. This is called without a zero divisor. A not equal to 0, B not equal to 0, the product AB not equal to 0. This is called without a zero divisor. For example, 1 not equal to 0, 5 not equal to 0. The product 1 into 5 not equal to 0 is 5. Is not equal to 0. This is called without a zero divisor. You take any example, Z6, Z4, 4, If we take non-zero element, product should not be appear 0. That is called without a zero addition. Suppose if we take one of them is 0, and one of them element is 0, the product is 0. This also is fault here without a zero addition. So I go for the refer these textbooks in Erskine, Perle, and Michael Artins, Joseph Gallens.